Okay, good day, everyone. You are welcome to the last section of this series. We're still working on design and simulation of electronic system using implementation of 5-volt DC power supply for microcontroller applications. That's a case study. Let me share my screen so we can proceed. Confirm you can see my screen. Confirm you can see my screen.
Yes, I can see it.
Okay. So we are in module 3. Quickly, we are going to look at system simulation of 5-volt DC power supply. We are going to see how the component is going to be connected on breadboard and tested and then validated. Before we do that, we still do a quick introduction of our team. My name is Engineer Dr. Kenesa Marimbon. As at the time of this reporting, I'm a senior lecturer at Federal University of Technology, Owerri, Nigeria. I am going to call one of our team members to introduce the rest of the members. Gospel, over to you. So I am pointing the mouse. He will do the introduction.
Okay, good day everyone. Um okay, we have from our lecturer we have engineer Dr. Ekene Sonu Mbono. Then beside him we have Mr. Obi Prince Chukwemeka. Then beside Mr. Obi we have Mr. Barry Elf Daniel. Then the other side of Mr. Engineer Dr. Mbono we have Miss Anyanwu Faithful Chinaza. Then beside her, we have Mr. Lucky Ifeanyi Chidera. Then beside him, we have Mr. Chibike Peter. Then finally, I myself, Mr. Okechukwu Gospel Chibike. Thank you, everyone.
Okay, so thank you for that quick introduction. We go over to our module 3. Okay, so we're looking at simulation of 5-volt DC power supply for microcontroller applications. Well, the software we are going to use for the simulation is Proteus Design Suite. And then we're going to use a step-down transformer, 240 to 12 volts AC. The diode is IN4007 with peak reverse voltage of 1000 volts. We're going to use an electrolytic capacitor rated 1000 UF 25 volts. Regulator, as you know before now, is 7805 because we want to get 5 volts that can be used to power microcontrollers. Our LED will be red color. We're going to use connected LED in series with 1 kilo ohm resistor at the output for an indicator. We're going to use DC voltmeter, virtual DC voltmeter, and oscilloscope as our measuring instruments. here we are. This is the schematic of the design. To put this up, one needs to go to Proteus and pick up all these components. Picking them up is quite simple. It's not a difficult one. It's just to know what to do. So if you want to pick any components, you simply type, go to P and type the component. For example, you want to pick a transformer. You just type transformer and pick the one that suits you. There are many of them. You will pick the one that suits what you are doing. It's center tab. So the one we pick is this. And then you can continue to pick every other thing you want to pick. This is AC voltage source. Anyone you want to pick, you double click on it so that it appears on this component section. You want to pick a diode, just type diode, or if you know the number, you type it directly 4007 so that you don't waste time looking for it. You just type the number, if you know the number, and then pick the one that has a model, double click on it, it goes to the left of your component section. That's how all the components here are picked. For the instruments, you go to instrument section, you can pick your oscilloscope, okay? You can pick your oscilloscope and you can pick your DC ammeter, but we didn't use ammeter here. You can pick your DC voltmeter and any other thing you want. You have logic analyzer, you have virtual terminal, just to let you know that Proteus Professional Design Suite is a great software for electronic simulation. So here we are. After picking the components, you can actually connect them together. For example, if you pick a diode and you drop it, you click and drop. You pick another thing, you click and drop. If you want to connect anything, you just click on this and connect them together. And at the end of the day, you are supposed to link your system design to the ground of the virtual software. You pick your ground and connect everything together as we did in this circuit. So that's that. So that's the ground. Let me clear this off. So this is the simulation setup from the AC source. AC source is characterized to be 220 volts and 50 Hz. The transformer is characterized to mimic our transformer. 220, we want to step down from 240 to 12 volts. Somebody calculate 240 in the ratio of 240 to 12 is what ratio? (240) is to 12. Simplify it to the smallest number and tell us the number, tell us the value. Anybody? I hope the student can hear me. Is Obasi there? Is Daniel there? Is Gospel there?
240 to 12. 240 to 12 is 20:1.
20:1. So let's get
Yes, sir.
the proportion 1/20 is what?
Sir?
1 over 20. What is the value of 1 over 20?
The decimal value or the
The decimal value, 1 over 20. 1 divided by 20.
okay,
0.0.
1 over 0.05.
Yeah, I wanted you to see how the transformer was characterized to be a step-down transformer, because the 220 or 240 we're talking about is the primary winding. You're going to go into the primary winding, which is 1 Henry here. Then the secondary winding will be 0.05. Coupling factor is the same. Then the primary resistance of the primary winding is, if it is 1 M, then the secondary resistance should be 0.05 in the ratio we just calculated. Is that clear to you?
Yes, sir.
Okay. So that's how the transformer is characterized. We go over to diode. Diode, the name is already there. The label is there. If you want to change it to another label, you simply change it to any other thing. It will follow what you have labeled, but that is not what we intend to do. That's that. So that's that. I mean, if I want to change this, I can call it D10, and it follows me. But that is not what we intend to do. We've already labeled D1, D2, D3, D4. You also characterize your capacitor to what you want. If you don't want 1000 UF, you can give it any value based on your design calculations. And of course, what informs the choice of your capacitor is the ripple voltage you are expecting. We demonstrated earlier that with 1000 UF, the ripple voltage is almost zero. The primary objective of filtering is to remove the ripples. So the smaller number or the lower the value of ripple, the better for your circuit. However, you just have to be very careful so that this is what is coming out from here. It says it's step down is 12 volts. So you don't have too much ripple that will go below 7. So because this is 7805. You wouldn't want to have a voltage below 7 at the input because it's going to affect your output. These are some of the things we take into considerations before we choose the value of capacitor. Just choose the value of capacitor that is good enough, whose capacitance is good enough, high enough to reduce your ripple to as low as possible. Another consideration while choosing capacitor is the voltage rating. If here is 12 volts, it is not advisable to use 16-volt capacitor here, because definitely as we are going to see later, that what is called capacitor action. If here is 12 volts, by the time you connect to a capacitor action will increase the voltage, make the voltage should be a bit bigger than the normal voltage. So if you use 16 volts here and the expected output from your transformer is 12 volts, you are going to run into a problem because definitely you will be driving the capacitor beyond the rated capacity, and over time it's going to explode. That's that. This is your regulator. You can characterize it. It's already characterized just for you to name it. And then at the output, we can always zoom in and zoom out. At the output, we have our voltmeter, we have our LED, the output, this is what is generally called pin 3 VCC. We can label it VCC. We can call here VCC. And then increase here to about so that 0.18 so that it will be visible. So we can call here VCC. That's our 5 volts point. This voltmeter measures the voltage across the LED. This one measures the voltage across the resistor, while this one give us the value of VCC. The oscilloscope will help us to compare the value of the voltage, input voltage to the regulator, and output voltage. I hope we are together.
Yes, sir.
Yes, sir.
So once you are done with this characterization of your system, you run the circuit simulation and check your, look at it. So it's showing you the current direction and the positive terminals. So you can see that what do you call it? This is the input now. This is the input to the regulator. Very, very perfect DC input. And you have your output there. Now the meter will show us what the other readings are. But before that, let's try to reduce this value to let's say 10. And we simulate again. Do you notice there is a change in the repo now?
Yes, sir.
Yes, sir.
You can even see that system is no longer stable as it was. So please take note, the value of your capacitor should be high enough to give you a repo voltage that is very close to 0. Now, we simulate here. Let's keep this by the side. You can see that, let's check the output voltage. This is 2.82. 2.82. So that's voltage across the resistor. 2.20, that's voltage across the LED. When we go back to our slide, somewhere in module 1, we noted this, that the voltage across red LED is 1.6 to 2.0 volts. So this simulation is confirming that 2.20 is close to it. We don't expect 100% accuracy, but at least it shows us that when we connect red diode in this series, the voltage across it when it's working is about between that 1.6 to 2 volts. So that's that. On your own, you may want to change here to green, yellow, and see the effect. I mean, you can actually say LED, yellow. so that you get an LED that is yellow in color. Probably you come here, you remove this one and put that one and see what it looks like. That's all about science. You discover stuff. So it's like it's modeled the same way, but in the practical, in the reality, they may not be the same thing. Okay? So that's that. We take it back to what it was. We don't intend to change it. Now, let's note that Ohm's law, what is the challenge? What is it that I did wrong that made the system to show an error? Which one? Let's see. Is there anything I changed I didn't replace back? Let's see. Is it showing an error on this? Okay, this, that. Well, that's one of the, let me see. Let's see. Okay. So, what is 2.82? Add 2.82 to 2.20. What do you get?
We have 5.02.
5.02. And that's exactly what we have here. So which law does it prove? The addition of this is equal to this. Which law does it prove?
The current law, Kirchhoff's current law, right?
Current law
I think it's a voltage. I think it's a voltage law.
is a voltage law.
Voltage law.
Is a Kirchhoff's voltage law. Algebraic sum of voltage about a loop is equal to 0. So this is the source. This is the circuit. This is actually the circuit from this point, from VCC to ground. Look at the ground. That is the circuit. So the voltage, these two voltage is actually equal to the source, such that 5.02 minus 2.20 minus 2.82 must give you 0. That is Kirchhoff's voltage law. So that's that. This is the simulation of the system. Now we are sure our system works. The next thing is to breadboard it, and that's what we have here. That's what we have here. So at this point, this circuit is breadboard the way it is on the diagram. So this is a D what now? This is D1, D2. So this is D1, D2. What is it? This is D1, D2, D3, D4. And then you can see this is the positive of the circuit. This is the ground of the circuit. These are the AC inputs where the transformer terminals came in. This is our capacitor, 100 UF by 25 volts. This is our regulator. This is the 1 kilo ohm resistor. And this is the LED. You can see our team, breadboarding. Remember, we said that one of the things we do is capacity development. During the time of this recording, these students are 200 level students of Mechatronics Engineering, Federal University of Technology, Owerri. I'm sure, depending on the time you get this video, they must have advanced. They must have advanced. So, because the young shall grow. So that's that. You can see. You can see. Let's see what they are doing. Please confirm you can see the video.
Yes, sir, we can see the video.
Okay.
Yes, sir, we can.
Yes, sir.
So that is the circuit on the board. Okay, we progress. And then after that, the system was tested. Remember, we got 5 by simulation, we got 5.02. And by physical design, we got 5.03. So that's a good one. That's a good one. I think we need to clap for ourselves and clap for these students. Just a difference of 0.01. Is that correct?
Yes, sir, just the
Yes,
difference
sir.
of
Yes, sir.
0.0.
0.01. And if you convert it to accuracy, our system is 0. In fact, it's almost 100% accurate. Plus 0.5. If you want to convert check our accuracy, somebody do 5.03 minus 5.02 over 5.03 times 100 over 1. We want to check the accuracy of our design. 5.03 minus 5. Minus 5.02 over 5.03. We want to check the accuracy with respect to the simulation distance. We want to check the difference. We want to check the error. We want to check the error, the percentage error in the design, the difference, the percentage error. That's 5.03 minus 5.02 all over 5.03. What is it? I hope somebody is computing that.
Sorry, sir, my mic was on mute. I said I got 0.2. I did 5.03 minus 5.02 all over 5.03 times 100 over 1.
Okay, and you got what?
0.1988, which is 0.2.
Okay, so that is the percentage error. That is the percentage error. That is very small. It's very small. Okay. So that's that. We progress. So after that, we checked this is the voltage across the LED 1.85. 1.85. The simulated value shows 2.20. The design value shows 1.85. That is the voltage across LED, and voltage across the 1 kilo ohm resistor is 3.17. You can also add 3.17, add 3.17 and the 1.85. Let's see what it is. 3.17 plus 1.85. What is it?
5.02.
5.02. And what we got by reading, did we measure that? So 5.03. So 5.02 is still very much okay. Of course, the meter's accuracy come to play, but at the same time, we can see that Kirchhoff voltage law is achieved, and then we proceed. The rectifier output voltage with that capacitor was measured, and that was 12.64, and then that's 64 DC, and then rectifier output voltage with capacitor was measured. He read 15. We got 15.52 volt DC. You can see why I said earlier that it's not good to use 1000 UF by 16 volts, because this 15.52 is almost 16. These are the, if you have a rough idea of what you expect, if what you expect is very close to the rated capacity, you shift to the next range. That's why we use 1000 UF by 25 volts. If you are going to work, design, build a DC output that is very close to 25, then the next option is to use 35 volts, and etc., etc. This is the testing with oscilloscope and Arduino. So it was tested with oscilloscope. Our root mean square voltage was 11.89, and on the oscilloscope it is 12.2. That's that. The signal generator was used to make sure to check the oscilloscope to confirm that it is in good working condition before the measurement started. And then this is the output voltage. You can see after the rectification, the frequency is 0. Then VRMS, which is the same thing as VDC, average DC voltage is 13.9 as measured by the oscilloscope. That is unregulated DC input voltage to the regulator. Finally, the whole setup was mounted on a Vero board. That a Vero board was used. You can see the transformer, you can see the components, and then a switch was added to control the power. System validation, a blink, the whole idea is to show that, the essence of this validation is to show that the power supply can actually power an Arduino board. So what happened is that a blink program was loaded on this Arduino board and plugged to the laptop. Of course, if you are familiar with Arduino, you will know that once you plug it, the Arduino will get its 5-volt supply from the computer USB port. So the system was blinking when the Arduino board was linked up to the computer. Now let's see what happened when we connected the Arduino board to our own 5-volt design power supply. It's the same output. So this confirms that our power supply can actually power an Arduino board. Conclusion. I want somebody to read the conclusion for us. Is there anybody who has not spoken in this meeting? Justice, have you spoken? Justice is not there. Okay, Gospel, read the conclusion so that we can end.
Okay, good day everyone. Conclusion. This work demonstrated the basic approach. Sorry, by the way, my name is Mr. Okechukwu Gospel Chibikem. Conclusion. This work demonstrated the basic approach to electronic system development, starting from load analysis, component selection, system design, simulation, breadboarding, to mounting the circuit on Vero board. This is a very good start for beginners in electronic design, as the work lays foundational principles of electronic designs. Printed circuit board is a better technology for mounting electronic circuits. Thank you.
Okay, thank you very much. But this course didn't cover PCB, like printed circuit board. Okay. So this is end of module 3. Please subscribe to our channel if you have not done so. Like and share the video and answer the tutorial question. Always remember to tell us the location, your location. Thank you so much. And with this, we have come to the end of this series, design and the implementation of 5-volt DC power supply for microcontroller application or applications. We use Arduino Uno as a case study. This power supply can also use to power some other things. It depends on what you want. For example, if you connect a diode in series with output 5 volts, you have, if you connect a silicon diode there, you have stepped down that voltage by 0.7, which can actually help you to work with your ESP32 that works with 3.3 volts up to 3.6 volts. Thank you very much. We have come to the end of this lecture. For the students, do you have any question?
No, sir. No, sir.
Okay, and then for our
Fully
audience and
understood,
viewers,
sir.
if you have any question, you can drop it on the comment section. We will respond to that when we come online. Thank you.
Thank you everyone.